Right, guys, we have to face this direction because that monitor has network issues and cannot connect to it. So hopefully IT will fix it today, so next time we can use that one. And how many people have tried to access any of the links on the website? Does it work? Yeah. Okay. So that's important because if you look at the schedule here, there will be a quiz tomorrow, right, during the lecture, and it's on circuit basics. You can expect 7 equivalent circuits or superposition. So definitely study whatever the notes we have from yesterday. They'll have the video uploaded and have the notes. And homework 1 is due next Friday, which is fine. I mean, I think I posted to Canvas. Okay. So for the lab today, do you have any questions on anything? By far? Okay. So let's come back to the labs. I can see these are all the labs available on this website. I'm not changing too much. Just sometimes if some of the links have to be updated, I will do that. But this is the only page you are able to access to all the labs. If you click lab 1, I can see this is everything about the DAC, ADC, and DAC. However, it's just very beginning of the class. You know, all these files are available to you guys who are not really building the ADC or DAC. Okay, but the DAC it's just super simple, just the R2R string. I'm gonna show that circuit really quick, but it's basically just to try to learn how the LT Spice and Electro VLSI, which is this interface, how these two software work with each other. So Electro VLSI is a layout tool. It doesn't have a simulator, any simulation algorithm inside. So the simulator we are going to use is LT Spice. We have used that in circuit 1. So it's LT Spice for simulator, but there's nothing nowhere you can lay out a circuit in LT Spice. It's just a simulator, it's a Spice tool. For Electro VLSI, it's a layout tool, but doesn't have any simulation algorithm in it. So they are always separate, no matter what kind of EDA you are going to use. Even for the Cadence software in the future you are using for the later of the semester. It also has a layout tool called Virtuoso and simulation called Spectra. So they are all separate, always. I believe Electro VLSI is on the desktop. If you have a laptop, you can simply just download it from, it's open source. You can download it from the website. I think there's a link here you can follow. These are the older tutorials, not for the class. It's just for general purpose tutorials, which is this link. You click, you can find out, oh, the scroll bar here is so long. It's a lab embedded in the lab. But actually you are not going through every single thing in this web page. It's just a general purpose tutorial for how to make the connections between Electro VLSI and LT Spice. So if you open this website, you'll see all the links, where to download it. If you're using your own laptop, you probably need a Java to run this software. So go through this process, and there's something you need to notice. If you scroll down, can you open this link on your side as well? The most important part of this instruction is over here. Okay? So the error I have seen the most in the past semesters is that when people copy this command from here to here, they also copied the column. So don't do that. So start from this dash I, right, and the whole line here until L to this box. And for this one, so in the past when I installed LT Spice older versions, they directly installed everything to this path. However, in the desktop, in the lab, they may have a different path. First. Second, if you're using your laptop for the newer version of LT Spice, they may install it in a different place as well. And also for the executable file for the newer version of LT Spice, they could be different. So this one, you need to pay attention to it. most of the cases that you are not having the same executable file name here, and the path could be different as well. Okay, you need to update this one in this box. And for other things, just make the changes here, and these are not really tricky. Okay, and change the scale to 300 nanometers. I will explain why is that later, this maybe next week. So we haven't covered too much things yet, so this is just for you guys to follow. Okay, we're not designing anything, so and then you can stop right here. Okay, after this location in the tutorial, you can stop here and go back to the lab web page. And here's the file of the ADC and DAC connections, the circuit. You can directly download it and open it up in your electrical VLSI. Okay, so you can, these are easy. If you follow, you'll see the same view. And then you open it up, you can see there are so many files. So IC means icon, it's an icon file, and SCH is a schematic file. So most of the cases we in VLSI design, that's a very important concept that you guys are going to learn in this class. It's very, very similar to the other design strategies in embedded systems as well, like the IPGA, the different layers. So draw a schematic, for example, AND gate, right? So usually we will, let's say maybe a more complicated circuit, just more connections. And or, okay, so eventually this little circuit, this little module, is being put in a box. And we are just looking at the ports. So A and B are input ports, and X and Y output ports. So in that case, we are going, after you design the circuit, this transistor-based circuit. I don't know if I've learned that in logic, but I will just draw it really quickly. For example, the AND gate, it's two NMOS transistors on the top and two PMOS on the top and two NMOS at the bottom. So that's ground, and that's VDD. And that's A, that's B. So this is the internal circuit of the AND gate. ABX, so it's basically ABX. So all the gates, all the logic gates are built by transistors. So this is how you implement the AND gate using transistors. That's a two PMOS type transistors, two NMOS type of transistors. That's how you lay it out. And then you put in a symbol, and we call it icon in electrical VLSI, but we call it symbol in LT Spice. You can see an icon view, create the icon view, create a symbol. So there are different, there are same thing but different languages in the two different EDA tools. So this is the CMOS based transistor, and you have to build it in electrical VLSI as a schematic and put in the icon. So you have an icon of the AND gate. The same similar thing for the OR gate. You put the two gates together, you create an icon for these two gates. So it's, even though it's a really small circuit, but we still call it icon, or you can say this is the chip. So this is a module that you can reuse no matter how many times in the tool. So you place this one in the library in your tool, and whenever you need to use it, you just drag and drop in your design. So you can keep it consistent. Otherwise, you have to redraw it every time. So it's just not a good practice. Okay. And another advantage of doing this modular design is that you think about that. For example, this module is being used for 1 million times in the chip. The chip can integrate like millions, billions of transistors nowadays. So you're using like 1 million of them in your design. Okay. Is it better to use the same design for all these spots in the design, or you want to use different modules for the 1 million cases? it's probably the same stuff for all the million cases, right? Because whenever you have issues in the circuit, you just fix the original module you created, and then fix all of these ones being used in the circuit. That's another advantage of using modular design. So that's if you look at all these files over here, it's actually lower layer being wrapped by upper layer. It's just keep doing this. You can have thousands of layers. And you can see all these ones. There's a ADC file, but ideal IDC file. They're already created in the file you are going to download from the website. The DACs, these are other circuits, and some of them we're not going to use. And you can see this one is called SIM. That's a conversion of how to create a simulation file in electrical VLSI design or VLSI design in general. You can see that we have an ADC, we have a DAC, and we put them together to form one circuit. You'll see the circuit in the tutorial later. But anyway, so we put the ADC and DAC together as a circuit. We want to simulate that circuit. Okay. So then you need to create another schematic to simulate it, because all the simulations happen in the schematic. You put a voltage source over there, and you write your SPICE code at the bottom. Then you can create a simulation file. So the simulation files are also schematics. Just keep in mind. You are creating all these modules like this one in schematic, but also when you are running simulations, it's also in the schematic view. That's why it's called the SCH, schematic view for simulations. And for that, the naming convention for that is we put a SIM in front of the whatever circuit you are trying to simulate. Okay, so it's a simulation file. It's not a chip, so we are not creating an icon from this simulation file. It doesn't make sense to create an icon because that simulation file usually has a voltage source in there. It's like a voltage source, like a battery. I mean, when you are doing chip design, you put a chip on there's no battery, no power source in the chip. Definitely, right? So you just leave the ports available and connections available for the voltage source, but there's no actual physical voltage source in the chip. So that's why we run this simulation file. This simulation file will be a singular file sitting in the library without any other files with it for that library. You'll see this in the next few figures, I think. So this one shows you the circuit. Okay, Vin is I think the sine wave. Okay, so the sine wave analog input. ADC is analog to digital converter, so it's converting analog signal to digital signals. So digital signal is just the 1 zeros. Analog signal is just one sine wave or whatever analog signal that is. So analog in, digital out, it's a 10-bit ADC because you can see it's from 0 to 9, so it's a 10-bit ADC. Okay, and then we have all these 10-bit digital output being put in the digital analog converter. It's a DAC, which is the easier circuit. We're going to cover the circuit structure a little bit today and tomorrow. We're using the superposition theory to calculate for the calculation. And so the digital signal getting to the DAC. The DAC, the digital analog converter, is converting that digital signal back to analog. Okay, so you can imagine the output will be just one pin, right? But all these are 10 bits, digital pins. So the 1, 10, and 1. Okay, it's just for simulation. You cannot find any applications for this. Okay, this is what is this? That's a SPICE code. I covered a little bit yesterday. And what is this view? Icon, schematic, layout. That's a circuit schematic. And you can definitely run simulation in the schematic. So what is this block? What is this called? Icon. Okay? What is this? That's a VDD. Yeah, voltage source. That's a VDD. Why is it called VDD? VSS sometimes. VCC sometimes. And the transistor, based on the transistor's terminals. So VDD usually is for the CMOS technologies. The top pin is the drain. It's called a drain terminal. Drain starts with D. That's why it's called VDD as a convention. For VCC, for the older technologies, they're using the bipolar transistors as the collector on the top. That's why it's called VCC. But they are both power sources. And for the PCB design, usually we use VCC for some reason. I don't know why, but you just need to know that. When you see a VCC or VDD, you know that's a voltage source. Doesn't matter in IC design or PCB design. So for VSS, S stands for source. Source is the bottom terminal of the CMOS transistor. It's usually connected to ground. So that's why VSS is also being used in PCB design. VSS stands for usually being connected to ground. And what else? VEE. So VEE is for the bipolar transistor. It's also ground. Okay. So you see all the terminals. One thing it didn't tell you, but you need to know is if you grab a circle, this is a symbol from the library. You can directly drag and drop into your schematic view. So this thing, it doesn't have a name with it, but it's called VDD. It's just a VDD. The name of it is just VDD. It's a global variable, which means if you put a VDD in this layer, and if you wrap it with another layer or 10 more layers, it doesn't matter. This global port will be reported to the upper layer as well. But these ports are not going to be reported to the upper layer. So what does report mean? You'll get to that point later. But don't worry about that. So just keep in mind, VDD. If you name this pin as VDD by a text, you just type VDD there. It's going to be automatically shorted to this VDD. So that's the same VDD. Even though this symbol doesn't have a name with it, but it's the name of it, the hidden name of it is actually VDD. Same for ground. I don't have a ground symbol here, but if you type a GND, and it will be directly shorted to the ground symbol, even though we don't have a ground symbol used in the schematic. So why that is important? Because you can see here, VDD. That's a SPICE code, right? I run this example yesterday. So please let me know what are these, what does that mean? Or what, so VDD is what? In this SPICE code, if I put a V, so this is SPICE code, right? SPICE code. VDD is the name of voltage, all right? And this VDD is the name of the node. Remember yesterday? Okay, I showed you an example yesterday for the SPICE code. Right, so that's the name of the voltage. That's the name of the node. You can name the node whatever you want, right? It can be 1, 0. That's what I labeled over there. But 0 is always ground. Keep in mind, 0 is always ground. But for the other nodes, you can change the name of it. So it starts with the name of the component, and then the name of these nodes, and then the value. Okay. So if you come back to this one. So that's the name of the component, and that's the name of the node. This can be changed. It doesn't have to be VD. If you name it differently, like this one, if you name a different name, then you can change it here as well. 0 is ground. So this VDD has a voltage drop from this node to 0, and it's a DC 5 volts. So I'm saying, hey, DC, you don't have a DC over there in the example in the class. It doesn't matter. You can put a DC, you can ignore it, you can delete this DC, and directly put a 5. By default, it will be DC voltage. It's going to be a DC voltage. So this is another voltage. It doesn't show up in this schematic, but I think it's being used within these modules. And VGND is totally unnecessary because GND is always 0. You don't really have to declare it, but you have it. It doesn't hurt anything. So VGND is the name of the voltage, and from GND to 0. Like this, okay? And then it creates a sine wave for you. The name of the sine wave is Vin, and it's dropping from Vin to 0, which is that node to 0. That's the voltage drop of this sine wave voltage. And that's the DC 0, which is DC offset is 0 volts. So there's no DC offset being added to the sine wave. And then it's followed by the voltage of the sine wave, which is 2.5 volts. I'm thinking that it's not doing anything here, but it's actually adding an offset in this sine wave function for some reason. So I think this is swinging, this sine wave swings around 2.5 volts, and the amplitude is 2.5. So it's actually, here's ground, for example, right? So sitting in the middle of the 2.5 volts and swing that like that. So 2.5 volts high and 2.5 volts low. And but sitting on 2.5 DC volts as an offset. That's 2 megahertz. So in LT Spice, MEG, if you want to make a megahertz, mega ohms, or mega something, you have to type it out. You have to type MEG for mega. If you directly put an M, even if it's an uppercase M, it's considered as milli, not mega. Keep in mind. And you create a clock. Here's the pulse function we covered yesterday. Starting voltage, low, high, delay, rising edge, falling edge, on time, and period. This is something you need to know. Okay, you need to memorize. It'll be on the quiz sometime in the semester. Okay, you need to know all the arguments. Which argument should be put in which location in the pulse function. And transient analysis. So what is this one? The options plot wing size equals 0. Sometimes you see a weird shaped output. You put this command there, it just will fix it. I think there's a resolution fix for some mechanism. I don't know how that works, but it always works if you see a really weird sampling frequency. So don't worry about that. Just directly use it. For transient analysis, that's a simulation SPICE command, right? So you want to put a stimuli there, or for analysis command, which is a transient analysis, a time domain analysis, starting from 10 picoseconds to run it through all the way to 1,000 nanoseconds. And 10 pico for, no, that's not right. I think they added more arguments to this one. You don't really need that many, I think. You just need the 3 arguments: start, stop, and resolution. That's it. Yeah, but this is from the example. You don't have to change anything. If you want to play with it, you can just delete, modify this line, use the one I covered in the class, which will also work. Doesn't matter. So this one will give you the circuit connections, and then you directly run a simulation by clicking Tools, Simulation, and write a simulation SPICE stack. And it's going to show you this. Okay, so the blue line is the analog input, and the black one with the little stars is the output. Because you don't have an infinite resolution for the ADC and DAC, right? So eventually it's getting digitized and showing these little stars. If you have a better resolution, like this will have 10 bits, right? If you have 12 bits or 14 bits, the stars will be significantly smaller. But that shows you how that works. And if you can see this curve, it's a success for the first few steps. And then keep moving. It's asking you to build a DAC by yourself instead of using the DAC being provided. The DAC is way easier, just keep in mind. The DAC is just a resistor string. But ADC could be very complicated. And we'll keep using the ADC from the example, but just to replace the DAC being provided from the example. So you draw the DAC by yourself. It's just a resistor string. We'll cover the calculations on Wednesday. And you draw it, right, in this way. And you put it here and create a what out of it? That's a schematic, right? It's a resistor schematic. And you create an icon. Okay, that's an icon from this schematic. Why? Because this looks better. And some of the schematic can be huge. And you put an icon, it can be very small. And you just draw a box. You basically, when you are designing circuits in VLSI, you don't worry about the internal structure because they're already in there in the sub module. So what you care about is just the ports. Okay, just inputs, outputs. So you create an icon from it, and you are only using the inputs and outputs from it. So just create an icon and put the ports, make the ports available. So see here on the left-hand side, these are the libraries, okay, for the cells. So these are from the example, and you created this library yourself. You call it R2R ladder. It's a resistor ladder or string. So that's the schematic you created, the one I showed you, and this is the icon you have. And in the future, there will be another type of cell in this library for this cell, which will be LAY. It's going to be a layout, will be the physical chip circuit, physical circuit being put on the chip. So now we don't have that yet. That will be in lab 2. So you have a schematic, icon, and layout. And you can see these ones, right? So the simulation files, and they don't belong to any library because these are just simulation files. And we're not creating any circuits from it. It's just a schematic for simulation purposes. So these are single files. And we put a SEM in front of it. Again, these are schematics, SCH. So from the example, you delete the right part of the scheme of the circuit and replace it with your icon. So the way to do that is to directly drag and drop icon to here. A lot of people will forget how to do that. They're trying to like copy and paste and try to load it from somewhere. It's really interesting. Electrical device will allow you to do a lot of operations, but none of them will work. You have to follow the correct routine, which is, you go back. So you have this schematic, for example. You delete the right part, okay? The part on the right hand side. And then what you want to do is, still in that view, you click this icon, you click it, right, and hold it. And just drag and drop into the view. That's how you do it. Keep in mind. You can also load it from the top, I think, but don't do that. It just won't work. Okay, you want to drag and drop into your design. So this is the one I drop in here, and you make the connections. So after the connection is made, these labels will just disappear. And another interesting thing for electrical VLSI, which is naming all these wires, and they call the wire, even though usually it's a wire, it only happens in electrical VLSI. So they call it ARC, ARC for some reason, okay? And you see in your SPICE code, when you are trying to use a node, for example, VDD, and you have a node here to 0, right? So that node is actually the name of the arc, and the way to change that is Control I. So you left click, single click on the arc, and you press Control and I, and it's gonna pop up the window and let you change the name of it. So after change the name, it shows the name on the top of the wire or arc. So if you see that, that's a success. It's the same here. You can see that it's directly on the top of it. It's not at the bottom, not on the side, it's directly on the top of it. Then you run the simulation again, you should see the same results. So replace the ideal DAC with your resistor string DAC, and it should show the same result. And for this one, it's a simulation work at the bottom of the tutorial. It requires a little bit of calculation. So the resistor string for the DAC looks like this. I'll just draw 4 bits, because that will be too many of them. So this is the output of the DAC. Okay, and these are 2R. This is R. For example, 10K, and these 2Rs are 20Ks. Let's just label it 2R, 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 2R. Oh, sorry. And the DAC's symbol, for example, it looks like this. Okay, that's the icon of the DAC. Even though we have 10 bits in the example, but we are only drawing 4 bits over here. So in that case, we're naming this one as B0, B1, B2, and B3. And that's the output, that's the analog output. These are digital inputs. The digital inputs into the DAC, and this is the analog output. So if we ground all these inputs and give a signal here and connect the output to the load capacitor, we can easily draw equivalent circuit from this. And what that is gonna be. And you can see these, since I grounded all of these ones, so 2R, if you just look at this part of the circuit, you have two grounds, and 2R in parallel with 2R, if you look downwards, what's the equivalent resistance of the whole thing here? What's the equivalent resistance? We got 2Rs in parallel. What's the equivalent resistance? 1R, right? Okay. So if you remove this thing here, and it's basically a 1R to ground, and these two resistors forms another 2R resistor and ground it. And it's the same thing. If you look at this one, that's a 2R and that's a 2R as well. So for this whole part here, we'll have an equivalent resistance of what? 1R as well, right? So for the whole thing here, it's basically just the 1R. Again, same thing, 2R, right? 2R and 2R. So the entire part here is basically a 1R resistor. Okay, so the equivalent circuit of this entire thing becomes, you got a voltage source, it's giving you a pulse. It has a 2R resistor in front of it. It's directly shorted to a 2R resistor and ground to ground. And then at the output, you have a capacitive load. That's the equivalent circuit. You refer to the notes from yesterday, how to convert this one to this Stevenson equivalent, so we are getting an RC circuit. Right, you want to convert it to this. This is RTH, VTH. It's actually a VTH, yes. And this is C, right? It's a load, C load. Okay? You do this work, and then this is how I'm just, because there's no, this is a symbol, there's no internal circuits being displayed, but you know what's happening, right? So all these are being grounded, and that's the output, that's the capacitive load, that's the input, the same thing. So this circuit is basically this one, all right? This one, and convert it to Thevenin's equivalent circuit. You find out the R, find out voltage, and then you run the simulation in electric VLSI. So here's the spice code, right, provided. And you see that I have to name this wire as B9 as the arc, Control I to name it B9. So whenever you code it up in your spice, B9 will be recognized as the node on the top, and B9 to 0 is the voltage drop of this voltage, which is the pulse voltage. So that pulse voltage is being applied to B9 and 0. Okay, because it's ground. The pulse source is also a voltage source. It's being grounded, right? And then the output connects to B9. And then you do a trend analysis because pulses are in time domain, and it's just trying to make the plot nicer, looks nicer. So you run it, and you're gonna see this. Remember yesterday we covered that how to measure time delay. Okay, so you see an input. Even though it looks like it's just a straight line, but actually it's a step function. It's just the upper voltage is overlapping with the boundary of the graph. But it's a step function. The black one is the input. It's a step function. It's a pulse, and this purple curve is output. And you can see it's only half of it because the Thevenin is equivalent. It's VTH. The voltage source is smaller than that. Are you getting that? You see here. Your V in, you're simulating this circuit, not this. Okay, you're simulating this one. So V in, after the Thevenin's equivalent, you see it's being divided in two halves. So that's why the output here, the DC voltage, eventually will be 50% of it. And that's why the output is not reaching V in, it's only reaching 50% of V in. But that's okay. So when we are measuring time delay, we're only looking at 50% of the output voltage. So you bring up the cursor by clicking the name of the source. So you got a cursor, then you drag it to the middle. Okay, drag it to the middle. So it's targeting 1.25 volts because it's 2.5 volts, 50% of it. So it's 1.25 volts. It won't be accurate, you can see. It's 1.259. You can move it to make it as accurate as possible, but I'm getting 1.25 something will be fine. It's acceptable. Okay, and then you find out the corresponding X value, which is the time. You see this is a vertical value, which is voltage. Make sure it's 50% of 2.5 volts. And then you look at the horizontal value, which is the time. Okay? And then you compare this simulated time with your 0.7 RC. We covered yesterday, time delay. They have to match, okay? So in your report, you just say, hey, see, simulation results matches my calculation. So you put a 0.7 RC and for this equivalent circuit, because that 0.7 RC is derived from this single RC circuit. So you have to use the R and C here. Okay, 0.7 RC using the RTH and C. And simulation looking at here and compare. So the report will be, I recommend that you guys use, a lot of you use latex. I don't require latex at all, since I don't really use latex. A lot of people like to use it. I just use a Word document and plugging. So what I usually do is using snipping tools. This one. I make a snapshot, okay, and copy and paste to the Word document and put the descriptions, narratives above it or below it, doesn't matter. So put some description in there showing what this figure is. Just keep doing that for the whole Word document, convert to PDF and upload it to Canvas. So it's for lab 1, for the following labs as well, same thing. It's going to be a single PDF file being uploaded to Canvas. And that's the end of the lab. 100 points. Any questions on this? You can get started. I think the most tricky part is whenever you guys started doing that, you have to make the connection between LT Spice to electric VSI, which is the configuration I took about over here. All right, just be careful and be patient. Make sure things are right. Okay, you can get started.